So as you'd already be familiar with it, this is the mass energy equivalence expression. This is the mass energy equivalence expression. And it states that an energy of any object, the energy of any object, is equal to that object's mass times the speed of light squared. Which is, 3 times 10 to the 8th, a little bit closer to 2.99. Alright, so you'd already be familiar with that expression. And we're allowed to manipulate this expression. This expression is, at the end of the day, a tool. So I'm allowed to say things like 1 equals mc squared on E. I'm allowed to say things like 0 equals mc squared minus E. I'm allowed to say E on m equals c squared. And this last one is very important, because what we can do here is we can do sort of a proof for the proportionality of energy and mass. So any object's energy divided by its mass is always going to give us a given known constant solution, c squared. And then we can also take this a step further and we can say, well, what if I don't want to deal with squaring the speed of light? Well, you're going to have to deal with square rooting energy over mass. There's a proportionality between these two, between energy and mass. There has to be a proportion. As I increase my energy, say I have an object and I record it at rest after an event, and its resting energy is equal to E naught, and I realize that an event happened and this object must have moved with energy that was stored within the object, so now I find what this kinetic energy with which it moved is equal to, and now I have, now I have a new energy. Now I have E1, and I already know, because of my measurements, that its resting mass, its resting energy over its resting mass, had to equal the speed of light squared. Now I know E1, but I don't know M1. I don't know M1. Well, now what I can do is, okay, I've calculated for its E1, and I know what the speed of light squared is. You'd always know that because it's a constant. Now I can solve for my x. X equals m1. So m1 and e1 are the mass and energy respectively before this kinetic energy releasing event occurred. I can solve for x because I can sub in e1, and it's always in proportion. So if I want to increase my energy, I'll also have to increase my mass. So essentially what I'm dealing with here is not only an equivalence, that mass can be converted to energy and vice versa, and as energy is released, mass is lost, and as energy is gained, mass must also be gained. Not only am I able to say that, but I can also say there exists some kind of mathematical proportionality between the two. There is a mathematical proportionality between the two, because equations like E equals mc squared can be manipulated in such a way to produce these two equations, where there's a constant on one side and my variables can be input on the other side. So there is a proportionality between energy and mass. And that is what is being said here. And you can solve for unknown values of energy, and you can solve for unknown values of mass, given, at least one of the two. given you know at least one of the two, because at all times the speed of light and the speed of light squared will be constant.